My name is Daniel Connell. For the last 10 years I've been developing low-tech alternative infrastructure, basically things that people can make themselves from recycled readily available materials, which takes care of their basic human needs. This is mostly to do with energy, water and sanitation, food, that sort of thing. I'm at a place called Vaidara Labs in the hills of Barcelona, working with a group called Coact to develop a pico hydro turbine. So a very small scale, but very low cost and portable means of producing electricity from water. Basically right there. So the whole project has been open source, making things more accessible. Theoretically, anybody, anywhere can make this stuff and get access to these resources. There's a bit of optimization is going to start rapidly paying off. So we're going to try again with two different approaches. A basic computer fan. Plan B.5 is this impeller design, which we're going to now 3D print. Okay, go. So this is the phase 3 turbine. It's similar to the previous ones that we tested. I am going to flip it around direction-wise though, so that the water is going to come in from here. So this will be on, so we're going to move it to further down the canal with about like a 2.2 meter drop instead of the 0.9 meter drop, which should give like 3.5 times as much power overall. So the water's going to come up here, go through here across the top of the weir and then vertically down. This is going to be horizontal and then the water's going to come up this way and turn the fan in that direction, and then pipe's going to plug in here up on the floor. Other than that, it's basically the same. So we're going with the unreinforced PCU fan because it did the best revs. The 3D printed impeller did a good job. In terms, it did more torque with less revs. I want more revs with less torque. I don't want less torque, but I want more revs because that means more voltage, which means less transmission losses and stuff. Sorry.
Don't worry. Tell you what then.
Wow, water and some level of toxic waste.
Water from the Anoya River.
Yeah?
Yeah. Wow!
Loco! Vamos!
Holy shit!
Yeah.
So fast! Super!
Bien. There we go. That's the number. So, if we can get 10 amps off this hoverboard wheel, which it should be rated to, times 55 volts, if there's enough power in the full system, that means we could, without melting or damage anything, getting about 500 watts off the system quite easily. If there's enough water flow, but there should be, because like the full system power of this is about 1.2, 1.3 kilowatts. So even if we're only going at like 40% efficiency overall, which is hopefully more, that's still like 500 watts right there. So that times 24 hours a day is 12 kilowatt hours, which is enough to run about 2/3 of a Western suburban home. Everything here cost about €40. So like what we've got here in terms of water availability is quite good. We've got this like long vertical drop, we've got like a really solid water supply here. Most situations aren't going to have something quite this good. This is a good situation, but it's also a lot of power. So in other sort of like in places where you've got like little streams that come down a couple of meters on an angle, this will do a lot less power, but it'll still do useful amounts of power. Especially if you're camping, make a little portable version. Especially if you're living in the developing world, the global south, then this, I mean, what's coming out of this right now will power like, I don't know, like half a dozen homes in like a developing country, easily, and cost less there than it did here because generally materials are more cheap. But this is all very, very standard stuff. The hoverboard wheel, not so much. Everything else you can get anywhere in the world. This can get swapped out for a motorbike alternator or something similar to that, which is available anywhere in the world and will do fairly similar amounts of power and voltage per rev. So next we'll wire it up. That'll be on these guys here at Califor to have to design a system for themselves, which is kind of like do what they want it to do, wire it in, and then we'll start getting some numbers, some data, and that can be broadcast. Once this has been going for a while, and as long as it doesn't break, I mean, we still need to like burn this in, obviously, over like days and weeks and months. But if it does all hold together, if it does seem like it's a fairly optimized design, then I'll be doing a full 3D animated construction tutorial, how to build the thing itself, and then everyone can make one if they want one. So basically this is a very good result. This is a very good result. I'm pretty happy with this. Alright, let's see how easy this is. Yeah, pretty easy. There she goes. With the previous test, the propeller was down the bottom and the water was coming down past it, which is generally how these things are done and feels more intuitively like how a turbine should be. With like a Pelton or a Turgo, like the more usual like 20 meters, 100 meters of head, running a bunch of pipe and having like a jet of water onto like a spinning like turbine wheel, then you need to put the turbine at the end, obviously, because that's where the pressure is at the bottom. But that's not how this turbine works. This turbine works by getting as much water moving as quickly as possible. Not like the pressure difference between the start and the end isn't where the power is coming from. The power is coming from the momentum. So it's more like a wind turbine in principle than a water turbine like a Turgo or a Pelton.